My name is Andrew Jackson. I'm a geologist with Global Resource Investments, and I'm responsible for technical evaluations of the mineral companies and their properties that Global invests in. I put together this Ore Deposits 101 series of talks to help non-technical people understand ore deposits. The talks highlight some of the features of the main deposit types that investors in the resource sector may come across, and provides an introduction to the jargon you will find in press releases put out by exploration and mining companies. This is the fifth in this series, and it covers epithermal deposits. Epithermals are a fascinating group of deposits, as you can virtually see them forming today simply by visiting hot springs like those at Yellowstone in Wyoming or Rotorua in New Zealand. This photo is the Pamukkale low sulfidation hot springs in Turkey, with their beautiful white sinter terraces. If you like hot springs, you'll love epithermals. Let's start where we always do in this series, showing how epithermals fit into the overall scheme of things. You'll remember that nature concentrates the metals by a process of partially melting crustal rocks at depth, letting the melt rise through the crust and cool, dumping the valueless minerals such as feldspars on the way, and concentrating the useful metals in the remaining magma or hydrothermal fluid. Cool, dump the dull stuff, and skim off the useful metals. The word epithermal comes from the Greek words for nearby heat, referring to the fact that epithermal deposits form very close to the surface of the crust, by definition within 1,000 meters. Temperatures at these depths are generally somewhere between 100 and 300 degrees Celsius, and pressures are much lower than deeper down, so that the fluids are sometimes able to boil. There are several types of deposits that form in this environment, including coal and gold deposits, but this talk will focus entirely on the precious metal epithermal deposits. Now at the start I must acknowledge the huge contribution from Dr. Antonio Arribas, whose presentation forms much of the basis for this talk. During the talk I'll describe the close association of epithermal deposits with nearby porphyry deposits, where we find them globally, and show why epithermals are economically worth paying attention to. The bulk of the talk will cover the different types of epithermal deposits, how each of them are formed, and I'll finish up as usual with a short section on how we explore for these deposits and a summary of the key points to take away with you. To understand epithermals, we really need to recap stuff we talked about in the third of the Ore Deposits 101 talks, which covered porphyry deposits. So please bear with me for a couple of minutes if you've already been through that one. Porphyry deposits form in large intrusions that acted as magma chambers feeding active volcanoes. You will remember that as the magma chamber cools from the outside inwards, barren feldspars and quartz crystallize out so that the remaining melt becomes enriched in metals and volatiles. The volatiles migrate to the top of the chamber and accumulate like the foam in the glass of beer analogy I used in the first Ore Deposits talk. Feldspar crystals take up more space than feldspar melt, and this, combined with the accumulating steam and gas, builds up pressure inside the chamber until the surrounding rocks can no longer contain it. The cool, solid rind to the magma chamber and the country rock above it rupture, and the volatiles escape upwards, carrying their metals with them. The metals then drop out of solution as the escaping fluids cool. Eventually those fluids reach the surface as hot springs. In this talk we're interested in what happens to those fluids and how they drop their lower metals to form epithermal deposits between escaping from the porphyry and reaching the surface. Epithermals are both genetically and spatially associated with porphyries. This is a section through the far southeast and Lepanto deposits in the Philippines, where this association was first conclusively proven. Here, geological detective work using isotopic studies and dating showed that the fluids from the far southeast porphyry escaped upwards and laterally to deposit copper and gold along their escape route, forming the Lepanto epithermal deposit. And here's a spectacular exposure of a porphyry and epithermal pair in southern Java. The porphyry intrusion outcrops as a small steep island on the right of the image, and a genetically related high sulfur Dacian epithermal deposit occurs on the mainland on the left of the image. Note that both here and in the previous case of Lepanto, the epithermals are not directly above the porphyry, but lie lateral to it, following the path of the outflowing fluids. We will come back to how epithermals form in a minute, but let me first talk about their timing in a global context. Although porphyries, and presumably epithermals, have formed from the Archean until today, the vast majority of preserved epithermals are relatively young, tertiary or later, i.e. less than 50 million years. Again, this sounds like a long time ago, but if we compress Earth's history into a single year, the tertiary would occupy just the last 3 days of December. Why this discrepancy between the ages of the porphyries and epithermals? It's all a question of preservation. Epithermals usually form in mountain chains and at shallow depths, so they are easily and quickly eroded, and so there are few old ones remaining in the geological record. So where do we find epithermal deposits? Well, obviously they are generally in the same place that porphyries form, in other words above subduction zones. And we can narrow down this a little bit more to subduction zones that have been active in the last 50 million years. This means we're looking at the so-called Ring of Fire around the Pacific Ocean, or the Alpine Himalayan plate boundary. Here's a map showing the location of significant high and low sulfidation epithermal deposits. You can see their close correlation with active subduction zones. Only a few of the deposits associated with older subduction zones, such as the Appalachians, have escaped erosion. You may also note the group of low sulfidation epithermals in Patagonia. These include Anglo-Serrano Vanguardia, Extorre Cerro Moro, and Goldcorp Cerro Negro. These are near the Ring of Fire, but they're not actually associated with it. Instead, they're due to a mantle hotspot that developed when South America and Africa were torn apart during the opening of the South Atlantic about 150 million years ago. These older deposits have survived erosion because they formed in low-lying area that was not subject to high erosion rates, and they are also further protected by layers of overlying volcanics. Why should we care about epithermal deposits? Well, they're a major source of gold, providing about 12% of the world's annual gold production. In fact, they are the second largest producers of gold globally after the Witwatersrand deposits. Now, I've used the terms and phrases high sulfidation and low sulfidation and intermediate sulfidation in connection with epithermals, and it's time that I explained this subdivision, because they're very different beasts, and you need to understand their characteristics if you come across them in a press release. If you understand their geological characteristics, it'll help you put the exploration results into context and help you make a better investment decision. So what are the differences between low sulfidation, intermediate sulfidation and high sulfidation epithermals? Well, the differing sulfidation state of the fluids associated with these deposits results in a very different detailed mineralogy that form the basis of the definitions. but you probably need access to an ore microscope or X-ray diffraction laboratory to identify many of these minerals. And most investors don't have these, so I'm going to not spend any more time on this aspect. Instead, I'll try and make it simple by talking about where and how they form. Here's a very simplified cartoon showing the two end members of the spectrum. Obviously, reality is typically more complex, but this works fine as a first stage approximation. Fundamental genetic difference between high and low sulfidation is the amount and degree of interaction between the magmatic fluid, groundwater, and host rocks. High sulfidation deposits form in geothermal systems where hot, acidic hydrothermal fluid directly from the intrusion remains undiluted by groundwater. Low sulfidation deposits, on the other hand, form in geothermal systems in which the magmatic fluid is cooled and diluted by groundwater, and the pH is neutralized at depth. The formation of epithermal deposits is all about dropping the gold from solution before it reaches the surface and escapes to the atmosphere or hydrosphere. How this deposition occurs varies according to whether the gold is being carried by hot acid fluids or cooler neutral fluids. First, let's look at the high sulfidation epithermals with their hot acid hydrothermal fluids. This is an aerial view of a typical bleached high sulfidation alteration zone in the Chilean Andes. In high sulfidation deposits, the mineralization is a two-stage process. Initial alteration, followed by ore mineralization itself. The cartoon shows the alteration stage, with hot acid fluids, sometimes vaporized, rising above the source intrusion and attacking the country rock as it passes on its way to the surface. The rock is progressively leached and altered so that the feldspars break down to clays, and these clays are then removed, leaving only a silica sponge which is impervious to hydrochloric or sulfuric acid. This silica remnant is often referred to as vuggy silica or vuggy quartz or lithocap. The second and third cartoons show the deposition of the gold. This often occurs in two phases again: an initial gaseous transport of the gold, and then, as the system cools, the gold comes up in a liquid phase. In many cases we don't get the second stage, and we end up with a barren leach lithocap of advanced argillic altered rock. Here's another cartoon of the same process, but showing how the shape of the plume of alteration and the mineralization may be affected by local geology and groundwater pathways. I promise not to go too deeply into the mineralogy, but you may well hear geologists talking about alunite. Alunite is a pink alteration product of feldspars, and it indicates that the fluids were highly acid. Its presence is indicative of a high sulfidation epithermal system. Active high sulfidation hot springs are not places you'd like to swim. They're acid and they stink of rotten eggs from the hydrogen sulfide. And because the acid breaks down into feldspar, breaks down the feldspar to clay, they usually consist of more of mud than of water. But how do you know when you're standing on an extinct high sulfidation epithermal system? The obvious diagnostic features are the presence of vuggy quartz, an abundance of white clays, and the minerals alunite and jarosite, which tell us that the fluids were highly acidic. And a lack of obvious veins, because in these deposits fluid flow relies on the porosity that the acid leaching imposed on the host rocks rather than on faults. Due to their disseminated style of mineralization, high sulfidation deposits are generally mined as open pits. Well-known high sulfidation epithermals include Gold Corp's El Sal in Mexico, Barrick's Purina and Newmont's Yanacocha, both in Peru. This is an old photo of El Sal looking south, before they started the mining. The vuggy silica makes up the cliffs due to its hardness and resistance to erosion. The light color of the drill roads is due to the white clay in the argillic alteration. In this plan view of the same deposit, the mineralized silica is shown in red, and the clay alteration is in orange and in yellow. In section, the vuggy silica in red can be seen to have developed in a gently dipping, favorable horizon in the volcanic stratigraphy. At Purina in Peru, you can clearly see the association of the gold, which is the heavy black lines on the image, with the silicic alteration in red, although it also extends out into the advanced argillic in orange. In this section of Purina, you can again see the way that the alteration has followed a subhorizontal, favorable stratigraphic horizon. This is the alteration map of the Yanacocha district, the mother of all high sulfidation deposits. The alteration system is 16 kilometers across and covers over 50 square kilometers. And again at Newmont's Yanacocha, there's a combination of both flat stratigraphic controls and steep structural controls to the silica alteration. So does the size of an alteration zone reflect the size of the gold deposit? It looks like having a large advanced argillic zone is a necessity for significant mineralization. But not all big alteration zones have gold, probably because they went through the leaching phase, but not the later mineralizing phase. This is critical to keep in mind when reading press releases, which extol thick intercepts of vuggy silica. They can still be completely barren. Okay, enough on the high sulfidation systems. Let's look now at the other end of the spectrum, the low sulfidation epithermals. Although they are a product of the same igneous system, low sulfidation epithermals are very different. In low sulfidation epithermals, the main control for gold deposition is fluid boiling, caused by a drop in the confining pressure as the fluid approaches the surface. This is a cartoon of a simple low sulfidation vein system, with all its components preserved. The fluids flow up a single, well-defined structures that blossom out near the surface. Alteration is not nearly so pervasive as in a high sulfidation system, and seldom extends far beyond the structures, unless there is a permeable horizon, and then the fluids may expand along the structure. Unlike the muddy acid waters of high sulfidation systems, the low sulfidation fluids are usually crystal clear and have a neutral to slightly alkaline pH. They look good enough to drink, but often have high silica, mercury and arsenic contents, along with the gold. When the water reaches the surface, it flows out and cools, allowing the silica to drop out of solution to form hard siliceous sinter terraces. Low sulfidation veins are usually well banded, often with alternating layers of silica and carbonates, and they frequently show brecciation or open space filling. More importantly, they may show plates of silica replacing calcite, which indicates that the fluid boiled. This is just what we're looking for, as boiling is critical for gold deposition. As in certain other deposit types, the gold in low sulfidation epithermal fluids is being carried as a thiocomplex with sulfur. Now I've lifted this slide from an earlier talk on greenstone shear zone hosted gold, where we covered various ways to drop gold from a thiocomplex solution. I won't go through this again in detail, but one of the key ways was to break the gold-sulfur bond by allowing the fluid to boil. This is the main way in which gold is deposited in low sulfidation epithermals. A reduction of pressure, allowing the previously pressure-constrained fluids to boil. The boiling zone, as it is called, begins at a certain depth below the water table and may extend up to the water table or die out before then. In the zone you'll see this evidence of boiling, and this is where the gold will be. Below the boiling zone, the gold will remain soluble and not be significantly deposited. Above that zone, much of the gold has already dropped out of solution, and the lack of boiling prevents any remaining gold from being deposited. Obviously, it's critical to the economics of a deposit whether the boiling zone has a wide or narrow vertical extent. The width depends upon a number of inputs, including the temperature of the fluids, the amount of groundwater mixing, the rate of flow, and the longevity of the system. So boiling zones can be anything from 50 meters up to 800 meters thick, with an average of about, say, 300 meters. The Pachuca low sulfidation deposit in Mexico has been mined for many years, and so there's plenty of data to build up a picture of the variability of the boiling zone. The thick black lines in this image represent the vertical extent of the boiling at various points along the strike of the vein. You can see that in this example there is a single boiling zone that averages about 400 meters thick. You may hear the word telescoped used in epithermal deposits. This means that the boiling zone moved during the life of the system, spreading the boiling zone over a greater vertical extent. Here are some better known low sulfidation epithermals that you may have heard of. You'll notice that, although some of them are typical vein hosted, there are some that have developed in more porous rocks and so are disseminated rather than vein controlled. Allied Nevada's Highcroft deposit in Nevada is a typical example of this. The Hishikari mine in Japan exploits a swarm of quartz carbonate veins. Mineralization is very recent, and hot water is still flowing from the rocks underground. Here's an underground view of the vein at Hishikari. Note the high grades, typical of this group of deposits. This is the Sleeper mine in Nevada. Again, although the average grade was low, some spectacular gold pockets were encountered. This is one that will be familiar to global investors, Esperanza's San Luis discovery in Peru. High-grade gold and silver mineralization occurs in the highlighted series of Arnechelong veins. Barrick's Purina deposit can be seen in the distance to the east. On the ground, the quartz carbonate veins look like this, erosionally resistant and just a few meters wide. The total size of the deposit is modest, but the excellent grades make up for this, with an average grade of 22 grams per ton of gold and 580 grams per ton of silver. Kinross and Barrick's Round Mountain mine is a 10 million ounce ore body, mined from open pit. Because of varying host rocks, there are both shallow veins and an underlying blanket of disseminated ore, similar to some of the high sulfidation deposits. A section through the mine shows the ore in red developing as veins in the blue welded tuff and as disseminations in the orange porous unwelded tuff and purple sediments below. The ultimate pit outline is shown as a red line. So much for the low sulfidation epithermals. Now let's quickly cover the last of the broad groups, the intermediate sulfidation epithermals. As the name suggests, they form partway between the high sulfidation and the low sulfidation environments, with a degree of dilution by groundwater but not to the same extent as in low sulfidation systems. They generally form veins and breccias like low sulfidation epithermals, but have coarser banding. However, they also contain alunite like high sulfidation epithermals. In addition to gold, they usually contain significant silver and increasing amounts of lead in the form of galena and zinc in the form of sphalerite as you go deeper. The gold and silver deposition is controlled by boiling. Base metal deposition is mainly by fluid mixing or cooling, because the base metals travel as chloride complexes, not thiocomplexes. Examples of intermediate sulfidation deposits include Mag Silver's Juanicipio deposit in Mexico, Kinross's Fruta del Norte deposit in Ecuador, and La Piteria in Mexico. At Juanicipio, the veins barely reach the surface, forming just the wispy siliceous zones you can see in this photo. But some 400 meters below the surface, the boiling zone is encountered, and the vein balloons up to 10 meters wide, with well-banded and richly mineralized quartz vein filling. The boiling zone has a vertical extent of 450 meters. Silver Standard's Piteria deposit is in Mexico. It was discovered by an excellent exploration team who looked beyond the low-grade and spotty geochemistry results from sampling surface outcrops, understanding that these deposits are vertically variable and that they were looking at the barren cap over a large, barely eroded hydrothermal system. Drilling has proven this to be the case, and this section shows how the system balloons out at depth. Most of the gold and silver mineralization is controlled by a shallow boiling zone, but the system becomes more base metal rich at depth, with lenses of massive base metal sulfides developed 400 meters below surface. The Fruta del Norte deposit in Ecuador was discovered by the junior explorer Aurelian. The mineralization does not outcrop and was found by drilling below a small outcrop of unmineralized sinter hidden in the thick tropical vegetation. In this 3D model of the mineralization, you can see steeply dipping structures in pink, with the multicolored prisms of mineralization in a vertically constrained boiling zone. The ore is well banded, with plenty of sphalerite and galena. Fruta del Norte has reserves of 6.8 million ounces of gold and 9 million ounces of silver, at a grade of just over 8 grams per ton gold equivalent, and a further 4 million ounces of gold and 8 million ounces of silver in resources. Okay, let's move on quickly to discuss how we explore for epithermal deposits. Many of the techniques are similar to those I've described for other deposit types. We need to start by focusing our efforts in areas where there is evidence of major felsic to intermediate volcanism, as it is this volcanism that drives the epithermal systems. We also need to find an area that has not been too deeply eroded, or else any epithermals will already have been removed. Multispectral analysis of airborne or satellite images may be able to detect wall rock alteration. Obviously, low sulfidation epithermal veins with their limited wall rock alteration will not be found like this, but it's a valuable tool for high sulfidation epithermals. You'll remember these images from my earlier talk on porphyry exploration. With exploration for high sulfidation systems, we're looking for the same sort of alteration as with porphyries, in other words phyllic, argillic, and an advanced argillic silicification. These show up as the pink spots on the image on the right. This is a similar multispectral image over the Goldfield area in Nevada, a typical high sulfidation epithermal system. The highlighted areas are where the ground exploration would obviously be focused. Once a clear area of hydrothermal alteration has been located, exploration moves to the ground phase, usually beginning with a combination of mapping to confirm the alteration and geochemistry to identify the best targets for drill testing. Remember that in epithermals we may have a significant vertical zonation, so that low grades at surface do not necessarily mean that the system is barren at depth. Here's the result of alteration mapping on the left and soil geochemistry on the right over the same area of the Bucket Hijau property in Indonesia. Note how the highest gold geochemistry on the right-hand image roughly corresponds with the presence of vuggy silica alteration, the hatched pattern, on the left-hand image. Because of the limitations of surface geochemistry, geophysics may also be used to identify buried vuggy silica or disseminated sulfides that may be associated with mineralization. This shows a series of IP traverses at Bucket Hijau, with the red high resistivity highlighting the vuggy silica in 3 dimensions. The final stage of exploration, as usual, involves drill testing. This is a core rig drilling at the Fruta del Norte deposit in Ecuador. This has been a long talk, but it's just about finished. Only 2 more slides to go, summarizing the takeaway points for epithermal deposits. So here are the key points to remember about epithermals. They form above or lateral to porphyry systems. They're the roots of old hot springs. Most are very recent, in other words tertiary or say 50 years or less. There are 3 main types and each have their own characteristics. Firstly, the high sulfidation. They're mainly gold with minor silver or copper. They can be very large, like Yanacocha, and they are often T-shaped due to control by steep structures and flat-lying host rocks. Their roots may extend to more than 1,000 meters in depth, although they're usually less than this. And they're generally low-grade with disseminated mineralization, so they're likely to be mined by open pit. Low sulfidation epithermals are mainly gold-rich. They have minor silver and mercury with them. They're usually small, though to moderate in size, but they're generally high grade and form relatively narrow, steeply dipping veins. The depth is limited by a boiling zone, which is seldom more than about 350 meters in vertical extent. They're likely to be mined from underground, unless there's a swarm of veins, in which case they might become open pit targets. Finally, intermediate sulfidation epithermals are gold-rich near the top, becoming more silver and then dominantly lead-zinc-rich at depth. Mineralization usually occurs in steep veins, but it may have flat splays, as at Piteria. The veins may be long and continuous. Silver, lead, zinc mineralization can extend to significant depths. For example, at Fresnillo, lead zinc extends from about 300 meters right the way down to 900 meters depth. Intermediate sulfidation, like low sulfidation, are generally mined from underground, although the flat portions may be open pitted as well. So that's the end of this talk on epithermal deposits. In the next talk in this series, I'll talk about another group of hydrothermal gold deposit that formed at shallow depth, the Carlin type gold deposits.